Welcome to part 2 of the animated earthquake PowerPoint. Hopefully you've watched part 1. If you haven't, I suggest you go back and watch part 1. Part 2 will make more sense after you've watched part 1. Okay, what we're going to do now is kind of look at actual examples of earthquake-related processes, and we'll begin with a brief case study of an actual earthquake that some of you might have actually felt. This is known to geologists as the El Mayor Cucapá earthquake. It occurred on Easter Sunday back in 2010 at 3:40 in the afternoon. The first thing to appreciate is it was a pretty large earthquake. It had a moment magnitude of 7.25, and like most earthquakes, it occurred along a plate boundary, namely the Pacific North American plate boundary here in Southern California. It did occur just south of the border, and it was a relatively shallow earthquake. It only occurred at about 6 miles below Earth's surface. And in that area, anyway, it was the largest earthquake to occur in about the last 100 years or so. So we'll just go through in the next few slides and look at some interesting examples of earthquake-related hazards, beginning with fault rupture. So this is a map of the faults that ruptured during that earthquake, the 2010 earthquake, the Baja earthquake. This is the epicenter of the earthquake, right there. In this case, this is just 2 different estimates of the epicenter. So that's the main earthquake. And then all of these other red dots in this case, red dots and red circles, those are aftershocks. Aftershocks are earthquakes in their own right. They're just earthquakes that are triggered by the main shock. And in this case, the earthquake ruptured portions of 3 different faults: the Borrego fault, the Pescadores fault, and also a fault that no one had even known about before the earthquake that was subsequently named the Indivicio fault. The rupture area was over 100 kilometers long, and that was seen from cracks that were literally mapped on the ground surface following the earthquake. Another way, though, to estimate the total length of the fault rupture, a kind of independent method, is to look at the length of the aftershock alignments. And what was interesting there is the length from the aftershock alignments was actually slightly greater than the rupture length based on measuring ruptured faults at the ground surface. And about a month after the earthquake, just under a month after the earthquake, I had the opportunity to go down to the epicentral region of the earthquake with a bunch of other geologists, led by kind of a world-class fault expert at SDSU, Dr. Tom Rockwell. So I'm going to show you some pictures from the 2 stops that we visited that day. So this was an amazing sight to see, less than a month after that big earthquake. This is a site where you can actually see the faulting on the ground surface. Each one of these cracks represents a fault, a fracture along which movement occurred. And what was really striking about this spot is that the earthquake itself actually bent the fence. So before the earthquake, this fence went straight across this area. And during the earthquake, the far side of the fence moved to the right relative to the near side of the fence, which moved to the left. And bottom line, it put a kink in the fence that could be measured. And so we know at this location, we can quantify the amount of horizontal displacement. It was pretty much exactly 1.2 meters. And by the way, these little tiny cliffs, if you will, these sort of tiny linear ridges where the fault intersects the ground surface and then offsets the ground surface, those are known as fault scarps. And so multiple fault scarps at this location. This, of course, tells us that the earthquake was big enough that it actually ruptured the fault plane all the way up to the ground surface. And then the other thing that was striking, too, is at this location, there wasn't just horizontal movement of the ground during the earthquake, but there was some vertical movement on the ground as well. You can kind of see that in these fault scarps. there's a little bit of vertical settlement, not just horizontal offset. So that was kind of interesting to see both types of offset, both types of shifting during or during the earthquake. So this was also an amazing sight to see. This is an example of a really, really young fault scarp. It's essentially 2 meters tall. There I am for scale, an earlier version of myself. And this is that linear ridge that stretched for miles in both directions that was created during the earthquake. Quite literally, the ground at my feet used to be connected up here before the earthquake. And then when the earthquake occurred, the fault ruptured. And remember, it's the fault rupturing that actually caused the earthquake. When that happened, this portion of the ground, known as the head wall, moved down in this direction relative to this other part of the ground known as the footwall. So that was an amazing sight to see. Here's another example of that fault scarp. It's this essentially linear vertical cliff that runs for several miles along the portion of the fault that ruptured. You can see it over here and then even over here as well. And again, just to emphasize the point, the ground right here at the base of the fault scarp literally used to be attached to the ground up here before the earthquake occurred. In other words, before the earthquake occurred, the fault scarp itself didn't exist. So what we're looking at here, here's the fault scarp, of course. And here on the head wall, there's a little tiny drainage, a little tiny stream drainage called a swale. And when we look for the swale sort of on the other side of the fault, we didn't see it there. We had to do some searching and found it right here. So in other words, the axis of the drainage itself was shifted by the earthquake, something like a couple of meters in this case. Okay, another serious hazard during earthquakes is not just the fact that the ground breaks and cracks and ruptures, it's that the ground shakes, sometimes very intensely. And that shaking is, of course, related to the passage of seismic waves, P waves, S waves, and surface waves. And it's that ground shaking that tends to cause most of the damage to structures and also infrastructure, roads and pipelines and bridges, for example. So that's what we're going to look at next, examples of ground shaking and building damage. So this is an earthquake intensity map of the fault area that ruptured. I mentioned before that the earthquake ruptured portions of 3 different faults, and that the overall length of the fault rupture was over 100 kilometers. Again, earthquake intensity tells you something about the damage associated with the earthquake. And even though this area wasn't very populated near the epicenter of the earthquake, it's been estimated that the shaking in that area was described as severe to violent, that had an earthquake intensity of 8 to 9, Roman numeral 8 to Roman numeral 9. This is the epicenter of the earthquake, and these values represent the percentage of gravitational acceleration experienced at different distances out from the earthquake. And right in the epicentral region of the earthquake, right there, the acceleration exceeded that of gravity, if you can imagine. There are very few buildings that could survive something like that intact. We know that because Dr. Rockwell, when he visited this area within a day or so after the earthquake, he noticed that there were rocks on the ground that had literally been tossed up into the air against the pull of gravity, and then in some cases landed a few feet away from where they were originally. So the shaking was quite severe in the area of the epicenter. And then, not surprisingly, as you sort of move out away from the epicenter, the intensity of shaking drops off pretty dramatically. So out here, for example, on the southern shore of the Salton Sea, right here, the shaking was only 20% of gravity. That's not too terribly much in comparison with 120% of gravity near the epicenter of the earthquake. And actually what I'm going to show you here, this is an incredible dust cloud that was captured on film at the moment that the earthquake struck. And so what's happening here is literally these mountains are moving up and down and sideways so violently during the earthquake that they kicked up these massive dust clouds. And some young people down south of the border happened to capture this on film during the moment of the earthquake. And I'll just mention very briefly that there is some adult language in this video clip, so be warned. So that was pretty incredible. Those power lines, by the way, that you briefly saw earlier in the video clip, a little bit later in the clip, which I didn't include here, the young people mentioned that the power lines were still swaying pretty violently. So that was a pretty serious earthquake to have generated a dust cloud that size. So just a few slides of building damage. In this case, in Mexicali, as a result of that 2010 Easter Sunday earthquake. Look at that, almost catastrophic damage there. This is a really good slide to emphasize why you shouldn't run outside of a building if you're indoors during the earthquake. There was some damage here to sort of the outside of the building, but notice that the building itself survived pretty intact. And yet, if you had run outside during the earthquake, you might have been crushed by this falling debris. That's a really good reason to stay inside during an earthquake if that's where you are. Another good reason to stay inside during an earthquake, sometimes the falling debris includes shards of glass. This is the inside of a shoe store. And even indoors, the biggest hazard you're going to face during the earthquake, the biggest risk to life and limb, isn't building collapse, it's falling debris. So particularly in California, most buildings can withstand a pretty good shaking. They're not going to collapse catastrophically. They're not going to pancake all the way down to ground level. But of course, if stuff is on the walls and ceiling tiles and chandeliers, light fixtures, et cetera, hanging from the ceiling, that stuff could fall on top of you during the earthquake. So this is just a short video clip to emphasize the point that the intensity of seismic shaking isn't just a function of how big the earthquake is. Now, sure, to a first approximation, as earthquake magnitude, that is, the size of the earthquake goes up, the shaking is going to become more intense, particularly near the origin of the earthquake. But this clip is going to demonstrate that a secondary effect on shaking intensity has to do with the sort of geologic substrate that the building is built on top of. So the take-home message here is that if you're on loose sediment, particularly if the sediment is water saturated, that sediment can shake harder and longer than hard rock, hard bedrock. Okay, sometimes what can also happen if you have steep slopes and weak rock is those slopes can give way either during or after the earthquake, creating a slide or perhaps a rock avalanche. That's collectively called mass movement. Just a couple of quick slides of, or quick slides of slides, two different slides in Japan as a result of a recent earthquake. And very briefly, what happens is before the earthquake, the hill may be quite intact, no problem, but during the intense shaking during the earthquake, existing fractures can be widened or perhaps new fractures appear, and that makes the hill greatly weakened. And even during the earthquake itself, or sometimes months after the earthquake, then a portion of the entire slope can give way, creating a mass movement. Okay, on to a process, a phenomenon known as liquefaction. At the beginning of the next slide, there's going to be a short video clip that explains what's going on, what's happening with liquefaction. Okay, as you heard in the video clip, what we have here is a water-saturated sandy layer at a shallow depth. And when the earthquake occurs, the rock on top sort of presses down on the sandy layer. In other words, the sandy layer settles a little bit as a result of this shaking. Kind of like if you had a jar of watery sand and you shook the jar, the sand would settle a little bit. It would compact. It would densify. So that's what's happening as we go from here to here. That's the condition during the earthquake. Notice now that when the ground on top is pressing down, water pressure inside the sediment increases, and that increased water pressure actually forces the grains further apart, so that now they're not really supporting one another. And the whole thing turns to mush. The whole thing turns to a liquidy material. And in this case, notice that the sandy layer is not horizontal, it's on a little bit of a slope. And so what happens when this sandy layer temporarily loses its strength is the layer above just sort of slides downhill. And in that process, this downhill movement produces mass movement, as the video mentioned, slides like we're seeing here. Mostly what we're seeing here is just sort of the downhill movement. And when that happens, these cracks get wider. That's a process known as lateral spreading. We'll see some examples of that in the next few slides. This is an interesting feature. This is a sand boil, also sometimes known as a sand volcano. And what happened here during the earthquake is that there was a subsurface layer of water-saturated sand that literally boiled out of the ground. And had you been in this spot during the moment of the earthquake, you literally would have seen an almost eruption-like column of sand, probably shooting several feet up into the air, that then fell back down to earth to create this, this sort of feature that kind of resembles a volcano. You can think of it as a sand volcano. This is in the Mexicali Valley, and again, what's happened here is the same thing that, that we saw in the last couple of slides. There was a shallow sandy layer that liquefied, and water was forced up to the ground surface, saturating the entire yard of this house. Notice that the house survived just fine. It was completely intact. That's a reminder that most structures aren't going to completely and catastrophically collapse during the earthquake, but in this case, it's the ground around and I'm sure underneath the house that essentially collapsed and liquefied. So it may well have damaged this house beyond repair. Same thing here. In this case, the car is, sinking into the liquefied water saturated ground as a result of liquefaction. And in this case, we're looking at a slight embankment here. This area, this material is moving down slope because again, there was a subsurface layer of sand that liquefied during the earthquake. And this form of mass movement following liquefaction is known as lateral spreading. So on that trip that I took about a month after the earthquake, this was our final stop. This is a dry lake bed just south of the Tecate border crossing known as Laguna Salada. And again, what happened during the earthquake is water in a liquefied sand layer underneath the lake bed migrated up to the surface to flood this area. And it so happens in this area that the water is salty from minerals that are washing into the lake from the surrounding area. And then by the time we got there 3 weeks later, the water had evaporated, leaving behind this rather extensive deposit of shoreline salt, all as a result of liquefaction. Okay, well, in terms of earthquake risk in California, it's a virtual certainty that we'll experience a large earthquake within the next few decades. And there's even a very high chance that it'll be on the southern San Andreas Fault right here. This is number 1 right here. This is the portion of the San Andreas Fault east of us, east of San Diego. And the scary thing is that this portion of the San Andreas Fault, number 1 there, hasn't ruptured since about 1720. So in some sense, it's overdue. The takeaway message from this slide is that big earthquakes are a virtual certainty in California in the future. Now, we don't know how big the earthquake will be. We also don't know where the earthquake will strike, and we don't know when it'll strike. No one can predict that over the short term, but certainly based on the past earthquake behavior in California, it's again, a virtual certainty that we're going to get big earthquakes in California in the near future. So that's a good reminder to be prepared. How can earthquake damage be minimized? Well, by preparedness. So to protect yourself, probably the most important thing to do, one of the most important things to do is just to know where all the potential hazards are in your home. Also, know how to shut off your utility valves, particularly your gas, and also have a plan. For example, my wife and I have agreed that if there's a big earthquake in San Diego, wherever we are at the moment that the earthquake strikes, we'll independently go back to our home and meet there. Even if we can't get into our home because it's been damaged, we'll meet outside. So those are just a few things that are good to do in terms of earthquake preparedness. This is an old home I used to live in. My kitchen. This would not be a good place to be during the earthquake because the biggest hazard, of course, isn't that the house will collapse, it's that falling debris will land on top of you. And just another reminder that you want to know where your gas and water and electricity valves are so you can shut them off. Fire is a really, really big hazard immediately following earthquakes because if the earthquake is a big one, the chances are fairly good that gas lines all over the city could be ruptured. Something else that's now required in newer homes is that hot water heaters have to be bolted to the wall, but it's possible that if you live in an older home, your water heater isn't bolted to the wall. That's a very good thing to do. It's easy to do, it doesn't cost very much, and it could prevent a fire breaking out after the earthquake. Earthquake kits are available online, but it's actually pretty easy to make your own. And the important message from disaster relief agencies like the Red Cross and other agencies is that after a big earthquake in California, expect to be without food and water and help from the authorities for a minimum of 72 hours following the earthquake. That means you're going to have to rely on what you have at home to survive during that time. That's why it's good to have an earthquake kit. And boy, the take-home message here, if you're indoors during the earthquake, the most important thing to remember, three things actually: drop, cover, and hold on. Remember, the building is not going to collapse on top of you. That's very unlikely, even in large earthquakes, in California anyway. But we know from studies of injuries during past earthquakes that it's falling debris from the ceiling and the walls that most likely will cause injuries. And so the best way to protect yourself from that falling debris is to drop, find a sturdy table or something, seek cover underneath that table, and hold on while the earthquake is shaking. Again, the table is not meant to hold up the roof of your entire building if it collapses on top of you, but the good news is that's very unlikely to happen in almost all buildings. So the whole point of drop, cover, and hold on is that you can protect yourself that way from falling debris during the earthquake. Just some quick stories that you can read on your own. This last one to me is particularly sad, and it really underscores why you shouldn't run outside during the earthquake. Somebody did in this case. They ran into the street and they survived the earthquake. Then they were struck by a car that was presumably out of control because the ground was shaking so violently. So if you're indoors during an earthquake, drop, cover, and hold on while the earthquake is happening. Here's another visual reminder why it doesn't make sense to run outdoors during the earthquake. Yet another reminder, look at this bookstore. You probably wouldn't want to be right here during the earthquake. Notice the building came through just fine, but many of the books fell off the shelves during the earthquake. Also, it's a long-standing myth that you should get inside a doorway during an earthquake. Doorways in modern structures are no stronger than the rest of the building, and there's also a good reason why they're significantly more dangerous than elsewhere inside the building. So imagine yourself standing in a doorway, and if there's a door in that doorway, think about what that door is doing during the earthquake. It may be opening and closing rapidly. You could get injured by the door if you're standing in a doorway during the earthquake. So what should you do during an earthquake? Drop, cover, hold on. I may make that an exam question. What are three things you should do during an earthquake? Drop, cover, and hold on. And then obviously after the earthquake, you want to check for injuries, check on those around you, etc. But the bottom line is there's absolutely no question that in the future, although we don't know when, damaging earthquakes will occur in California. Over the short term, they're completely unpredictable. So the take-home message here is we have to be prepared. Okay, thanks very much.